Okay, now we are. Here are the rules that we've done so far. Here are the rules we've done so far. And where did all of these, like, how did we derive them? How did we figure them out? We always started with what? Our rate of change function that we got from approach 2, right? The rate of change function. So here is don't try. This is what I went over last time at the end of, and we found that another. Here's the next rule. Our fifth rule was the square root of x. Its rate of change is 1 over 2 square root of x. Okay, but what is x as an exponent? What is radical x as an exponent? X to the 1/2, right? So we could use the power rule to do this. So we derived it with the radical, but we could just use the power rule. And what would it, f prime of x would be what? Or the rate of change of f with respect to x would be? Half x to the minus 1/2. Are those the same? They better be. Is that the same as that? Yeah, because x to the minus 1/2 is 1 over x to the 1/2, which is square root of x. Same thing, right? So 1/2 x to the minus 1/2, which would be like what you would get from the power rule, is the same as 1 over 2 radical x. They're exactly the same. So take your pick. So when I'm doing examples, we'll use this, okay? We'll use this form, but this is exactly the same. That's just using the power rule instead. Make sense? So that's 5. We got 5 of these shortcut rules now for finding the derivative, the exact rate of change function. All right, let's do another one. Exponential functions. So notice, not to be confused with, this is not equal to x to the n. Why not? This is totally different. Our input before was in the base. That's the power rule, when the input is in the base, and n is any number. But now with the exponential functions, our input is the exponent. Totally different kind of function. Totally different kind of function. So how do we start? Well, I want to know, I want to get everyone write it down. How do we start? We're going to try to figure out a closed form rule, a shortcut for finding the rate of change of b to the x. Where does that process begin of finding that rule? Everyone write it down. You should be able to write it down by now. Let's see who's on top of it. Josh, Kuzar, tell me, how do I get started if I wanted to derive a shortcut rule for the rate of change of b to the x? How would I start? Tell me for this.
F of x plus h minus f of x.
All right, so tell me for this though.
F of x minus f of x. F of x plus h minus f of x.
Okay, you want me to write that? Okay, f of x plus h minus f of x over h. Okay, now do the next step.
You plug in b to the x.
Oh, come on. Yes, you do. What does this say? It says take b to the input. So what's that?
You do the x plus h power.
Okay.
Minus b to the x power.
Okay.
Divided by.
I don't know how to do that.
You
Okay.
do.
All right. So remember our rules of exponents. We can change the form of this. What is b to the x plus h? There's no other way to write that. So b to the x plus h. That's like multiplying b together x plus h times, which would be like multiplying b together x times, and then another h times, right? Isn't that the same thing? B to the x plus h. Multiplying b together x plus h time could be like multiplying b together first x times and then multiplying by another h. minus b to the x over h. Are we good? So what can we do in the numerator? No, no canceling. There's no canceling here. We can factor out b to the x. And we're left with b to the h minus 1 over h. So I'm going to rewrite that as b to the x and then if we wanted to get exact rate of change, what are we thinking about for this? Making h very small, virtually 0, right? So, or the limit as h approaches 0. So let's work through it. As h gets very, very, very small, or h gets close to 0, what does that become? 1. So the numerator becomes 0, and the denominator is 0. So this thing right here heads towards 0 over 0. Just that part of it is like 0. And what is that? Well, this is called an indeterminate form. And there are 3 possibilities. Okay, that in some cases, according to what expression we're talking about, that might equal 0. In some cases, that might get really, really big. And in some cases, that might equal a constant, like a number, 3, 100, -6. So let's look at these 3 possible cases. If we had this case equals 0, then what would the rate of change be? Is the rate of change of an exponential function 0? No, can't be that. Make sense? That's out of the picture, right? Because if that fraction is 0, then the rate of change is 0, and that would mean that the accumulation function is a constant function. We know that an exponential function is not constant; it has a rate of change. Okay. All right. Goes to infinity. So number 2, this thing gets infinitely large, meaning the whole rate of change function is an infinite rate of change. Make sense? No, doesn't make sense. So what's left is that in this particular case, that 0 over 0 is a constant. So let's look at what we have here. The rate of change of b to the x is we'll just call it k for constant. So this is so what's going on here? The rate of change of the function is a constant times what? The original function. So this is a very special type of function. When you have an exponential function, its rate of change is a constant multiple of the original function, the accumulation function. Okay? K, yes, K for constant. And so it turns out, we don't have the time to show it, but it turns out that K is the natural log of B. All right, so to get the rate of change of an exponential function, it's just a constant times the current value of the accumulation. The constant times and that constant is the ln of b, the natural log of b. For all exponential functions, that's right. So that's what this is. So right here, as h gets very, very, very small, this thing becomes natural log of b. It's indistinguishable from natural log of b, right there. Can I erase? Okay, so let's write that out again. So We'll write it this way, but it's still the rate of change of f with respect to x is this. Rule number 5. Rule number 5. We got. What are we doing? We're building shortcuts to find exact rate of change functions. And every one of those shortcuts starts with our rate of change quotient, right? Our rate of change, constant rate of change quotient for some h. For some h. That's where we always start with those derivations. Okay, so now check this out. What if, so look at this. So find, let's say, p of x equals 2 to the x. So find the rate of change of p, or the rate of change of p with respect to x. Find that. And then say v of x equals 3 to the x. All right, and the rate of change of v with respect to x. So I want you to find both of those. Write them down, right? It's a piece of cake. What is the rate of change of p? Where is Rebecca Green? Where's Rebecca? Tell me. Rate of change of p with respect to x. She wants 2 to the x times the natural log of 2. What do you think? She did it, okay. And then this one would be 3 to the x times. I want you to find the natural log of 2 and find the natural log of 3 in your calculator. Let's get an approximation. So the approximation for the natural log of 2 and approximation for the natural log of 3. This one is 0.693 as an approximation. Natural log of 3. 1.098. Is that right? Is that a good approximation? Okay. So there's a very special base between 2 and 3. And such that what would happen? So here it's what, 0.693. So we're multiplying by something, we're making this value smaller. Here we're multiplying by 1.098. So we're making this larger. So there's something very special in between. What would be very special in between a base of 2 and a base of 3? What would the outcome be? So we'll call it z. Z of x something to the x times what would be very special. Here I'm multiplying by something that makes this less. It reduces it. Here I'm multiplying that makes it bigger. So in between, there's a very special, what would this value be? Would be very special. No, 1. And what would that mean? That would mean that the rate of change function is the same as the accumulation function. Do you see that? So for some base between 2 and 3, you're going to get the natural log is going to be 1. And what's going to happen? Your rate of change, this times 1 means it doesn't really matter. Then your rate of change function is the same as the accumulation function. Very, very, very special, right? That the output of your accumulation function is also the rate of change at that moment. Anybody know what that number is? Yeah, E. So E. So some number between 2 and 3 makes a natural log of 1, and that's E. And E is 2.7. 1828. Keep going. 1828. Keep going. 45904. 5. I don't know anymore. That's all I know. Okay. So this is a number very similar. That's the type of number that's like pi, right? It's a a non-repeating infinite decimal. And it's the special number between 2 and 3, that's a 1. It's between 2 and 3 such that the rate of change function, so if we have e to the x, the rate of change of e to the x is e to the x times natural log of e, but that's 1. So it goes away. So the rate of change of e to the x is e to the x. There's no other function in the universe like it, right? It's the only function such that the accumulation, the value of the accumulation, the y value, is the same as the number as how fast it's changing at that moment. So that's kind of like, what is that? It's like 6 rules now. This is a special case of our b to the x. So here is the rule, the general rule for all exponentials, and then when you have that special case e to the x, the rate of change is just e to the x. As a special case of that, a very, very, very special case. Okay, anybody have a question? Okay, this is what we said. Blah, blah, blah. Already did all that. That was our result we just came up with. Rate of change of e to the x equals e to the x. Okay, so here's what we got so far. 7 rules. Okay, so if it's b to the x, the rate of change is b to the x times the natural log of b. If it's e to the x, the rate of change is e to the x. It's the only function like it. It's the only function like it. Okay, and so there are many more that we're not going to talk about individually and derive. So do we have a... So here's all the single rules. Okay? Some of these we know, and some of them we don't. So let's just look at it. Constant function 0, x to the n, and okay, can I have your attention, please? You're going to have this. You don't have to. You're going to get this. You don't have to do that. X to the n to the x minus 1. Square root of x, 1 over 2 square root of x. A to the x, which we just did. A to the x, ln of a. E to the x, rate of change is e to the x. Okay, here's a new one. We won't derive specifically. The natural log or log function with base b is going to be 1 over x natural log of b. Okay, the natural log of x has a rate of change of 1 over x. Here's all the trig functions and their rates of change. So today, let's just jot this one down. We're going to use this one today. The rate of change of sine x is cosine x. Jot this one down. We're going to use it later today. The rate of change of tangent x is secant squared x. I think that's it. And then all of these. But for the mastery, you need to know them all. Okay? For the mastery, you have to have all these memorized.
So the root of sine x is cosine x?
Yes. The rate of change of sine x is cosine x. The ones I've circled are the ones we'll see later in class today. I think that's all of them. Maybe this one. The rate of change of cosine x, I forgot. The rate of change of cosine x is the opposite of sine x. So for class today, just jot down the ones that I've circled. The ones on the left we've already done. And then these 3 new trig ones. All of them you have to have memorized when we get to the mastery exam. Okay? These are all the inverse trig functions. Okay, you will be provided this list. This will be given to you. Okay, so memorizing these is easy. You could all do it in 15 minutes, okay? You could all have these memorized in 15 minutes. But so where it gets more difficult is when we have functions that are combinations of these functions. Sum, product, quotient, composite functions built on these, then the rate of change, finding the derivative becomes a complicated process when you have a complicated function that's a combination of these. So that's our next part of this journey is, of course, we have to memorize these basic ones, but then what happens when we get functions that are combinations of these? Then the derivatives start getting complicated, okay? So that's what we're going to work on. All right, so composite function is the process of executing two functions in succession. You take the output of the first, and you input it into the second function to get composite. When did we do this? We've done this semester. We took the output of one function, and we plugged it into another. We took the output of one. We've done this specifically. When did we do this semester? We took the output of one function and put it into another function. So what was it? So what was that? We took the output of which and put it into what? No, it had nothing to do with accumulation. We took an x value and we put it into what?
We did the step.
Yeah, so we took a current x value and we first put it into what? Left of x. And we took that left of x and we put it into the rate function to get the rate at the left side of the interval, right? We took x at the current x value, we put it into left, it gave us the x at the left side of the interval, then we took that and we put it into the rate to get a constant rate for the whole interval. So that's the idea of composition. Put in x, gave us the left side, and then we took that, put it into r, and we got r of x of l. And that's what built our step function. That was our step function. Okay, so what about rate of change of a function that's a composite function? These are all composite functions. They're like one function plugged into another. They're like g equals f of x. So for each of these three, I want you to determine what is f and what is g. And the answers can vary a little bit, okay? But what is f? X is initially going into what function? And then we're taking that result and putting it into a second function, which is g. So for these three examples, can you determine those two functions such that they equal g of f of x? Go. See if you can do it. Tracking there?
No. I wish I could say. It's like, I only see one formula. What do you mean by breaking one again?
So the idea is x goes into something, like here. You could think of x going into what function first?
Okay, we'll say that was f of x right there. Or m of x.
No, m of x is the whole function.
Right.
So what is x? What's happening to x first? How could we define an initial function that's operating on x?
Okay, it's cubed first.
Right. So you could say like we're cubing it. Then we're going to take that result and put it into what to get m of x?
Cube it, then we can subtract 5 and multiply the square.
So the input minus 5 square root. What function is that? The input minus 5 square root. So how would you write that? That's the first part. Input minus 5. Then square root. Anybody get it?
So it is just 2 steps.
F. Remember, it talks about more than 2 steps. X goes into F. The output of F goes into G. That's not the only way to do it. Yeah. Because f of g has to equal m. Or g of f has to be m. So we're going to take the output of f, and we're going to put it into g. So the output of f is x cubed, and we put it into g, and it equals m. So this has to equal this, or this, or this. Does it answer it? There's other ways to do it, yeah. X cubed minus 5 and square root of x works. Yep, that works too. Okay, do all three. Here? The 8th. Thank you. It's e to the 3x to the 8th. E to the 3x to the 8th. So, what could the initial function be? Not e to the. Not e to the. X is going into what first? X goes into what function first? Yeah, so we could do 3x to the 8 if you want. That's what how x is acted upon first. So the first thing that happens is we put x into 3x to the 8, then we take that output and we put it into what? The output of that goes into what function? E to the x. Is this making sense? Okay, what about this? X, what happens to x first? 1 over x squared you could do. That's one possibility. So you think about plugging x. What would you do to x first? That's f. That's the first thing that happens. Then we take the output of that and put it into what function? Sine of x. Is this making sense? You have to be able to identify these when if we're going to do derivative. Yeah.
It's just basically order of operations. I mean, the first thing you had to do was put x squared on 1, and then you have to go to that and put the sine.
Okay, if that, yeah. That explanation to someone who didn't know what to do would not help them. But if your mind is working, then that's good. Okay, so then the question is, looking back at m. What is the rate of change of m then? So here's a possibility. So we see that it's square root. So is it 1 over 2 square root of x cubed minus 5? Or maybe it's 1 over 2 square root of, so we're applying the rate of change to the square root and applying the square root to the middle, the undersection there. So here's, based on the rules we know so far, here are two possibilities for what we think maybe the rate of change of m might be. Okay, how can we check them? How could we check these two? So there is a way we know exactly what the rate of change of m is without knowing anything about composite functions. How can we know exactly what the rate of change of m is? What's our trusted form? Yeah. M of x plus. Yeah, so we know for sure this is right. With a small h, right? Very small h. Okay, so let's graph this. Let's graph this kind of open form version versus these two tries. And if we're right with one of these, what should happen? Should be the same graph, right? So I can graph it based on our quotient, our rate of change function, our rate of change quotient. And then we can graph these closed forms and see if either of them match it. All right, let's give it a shot. And this is a way that you can, when you're doing all these derivatives, this is a great way to check your answers, okay? All right, so what was m?
M of x is the square root of x cubed minus 5.
M square root of x cubed minus 5. And I want to graph y equals, I want to get the, what should I graph? Y equals what if I want to get the right rate of change function? I'm going to do m of, I want to graph the exact rate of change function. M of what? X plus h. Should all be thinking this right now. Minus. All over. Nope, want that. Divided by h. For h equals something small. Okay, so here's this rate of change function for this mx function, and we had a couple possibilities. Let's graph those and compare them to the red one. So what was our first attempt? Our first attempt is just use the square root rule and don't change the inside. How about that one? Is it right? Not right. If it was right, we should get the same graph, right? All right, let's try the other way. What's the next one we had? Let's do the square root rule. Y equals 1 over, doing the square root rule, 2 radical. But now under the square root, I want to take the rate of change also, 3x squared. And we'll do that. I'll make that black. How about that? So what? Which one do we trust? Red, blue, or black? We trust the red because we know that never fails us, right? This quotient, our rate of change quotient with a small h, will always give us the rate of change. We can trust that. It's when we start doing algebra and we start guessing, now we're not so sure, right? Because we could make a mistake. We could be wrong. So this attempt was wrong. That's the blue one. This attempt was wrong, the black one. So it's something else. It's something else. So let's see what that something else is. Here we go. Okay, so let's say f has a rate of change function, and at x equals 6.1, the rate of change of f is 3.8. We talked about this earlier. That means that if x changes a little bit from 6.1, y will change 3.8 times as much as that. That's what the rate of change value 3.8 means. Okay, so I can say that the change in output is about 3.8 times the change in x, or the change in output is r of f, 6.1 times the change in x. This is just what that rate of change value means. Okay, arguably, right, the screen, right, where you're looking at, arguably, like, if there were 3 things in the course I wanted you to come out with, one of them would be this. You understand what that number 3.8 is. That for a small change in x around 6.1, y is going to change 3.8 times as much as that. Rate of change. Okay, so here's a scenario. We've got the rate of change of f is 5 at a certain value, at 6. So when x is 6, the rate of change of f is 5. And the rate of change of g is 3. So now I want to know what's the rate of change of g of f of x. What's the rate of change of g of f of x at x equals 6? So we're going to let x change a little bit. And what comes first, f or g? What comes first, f or g? F comes first. How much will F change when x changes by a little bit? It'll change 5. Is that right? No, it will not change 5. 5 times as much as whatever little change of x we had. 5 times as much as whatever little change of x we had. So now that's a change in F, right? That's a change in F. And F is going into G. So how much is G going to change for that change in F? How much? 3 times as much as the change in output of F. So when x changes a little bit, F changes 5 times as much according to its rate of change. That's the change that is going into G. So now G will change 3 times as much as that. So going through the whole function, we start with a little change in x. How much will G of f of x change? How much will G of f of x change for a small change in x? Brock says 15 times as much. Because f will change 5 times as much as delta x. And then G will change 3 times as much as that. That's it. So if we change the input to G of f of x by a little bit, the output is going to change 5 times 3 as much, or this. R of f of x times R of G of f of x times as much as delta x. And that, in this case, is 15. Really important concept here. Do not wait for the punch. The punchline is that you understand this, okay? So this is K. This is the rate of change of G of f of x with respect to x. First, x goes into f, so it's going to change according to the rate of change of f, okay? And then that change is going to be our input into G. And so then it'll change according to the rate of change of G with an input of f. So in this case, the overall effect is that the output changes 15 times as much as the initial change in x. So this is, for a composite function then, this is how we calculate its rate of change. What comes first? F comes first. So the rate of change of G composed with f with respect to x is the rate of change of f with respect to x, the interior function. That comes first. Okay, if you're looking online at videos of other calculus courses or your friends, this is different than the way they're doing it. This is different than the way they're doing it, just as a warning, okay? You're going to look at the interior function first, and you're going to find how much does that change when x changes a little bit. And then you're considering that much change going into G. And then so how much does G change for that much change of f? So the rate of change of G with respect to f. And so you get this multiplying effect. So written with the prime notation, it's the same wording though. The rate of change of the composite function is, oh, I forgot to change them. Okay, so that's what that would be. The rate of change of f with respect to x, the rate of change of G with respect to f of x. So there's a definite advantage to doing it this way. When the problems get really complicated and long, I think this way is helpful. Okay, so back to this now. We said that. What was f? Let's say f is x cubed. And then g is radical x minus 5. So what's the rate of change of f with respect to x? That comes first. It's the rate of change of f with respect to x. We better know it. What's the rate of change of f with respect to x? 3x squared. What's the rate of change of g with respect to f? And so what is f? F is x cubed. So I want to do the rate of change of g with respect to f. So rate of change of square root is 1 over 2 square root. But not with respect to x, with respect to f of x. So what will go inside here? X cubed minus 5. Does it make sense? That was not one of our two guesses, right? That's why they were both wrong. Okay, this one, I'll settle. So we'll say, did we say 3x to the 8th here? Okay, you do it. And this one we said 1 over x squared, which is the same as x to the minus 2, and sine x. You do it. You do those two. Find the rate of change of p and the rate of change of q, applying our chain rule. E to the what? Not x. With respect to f of x. So it's e to the?
24x to the 7th.
No, 3x to the 8th. With respect to f. With respect to f. This is f. Not with respect to x. Not with respect to the rate of change of f. With respect to f. With respect to f. Questions on the second one? Did you get it? Third one. How's it start? Oh, rate of change of f. Negative 2 x to the minus 3 times
Cosine.
rate of change of that one with respect to f. Cosine of?
X to negative 2.
Questions on these? Anybody have a question? Okay, so let me have your attention. Let me have your attention, please. So I didn't get really nearly as far as I'd hoped today. So what I'm going to do is I'm going to make a little video, maybe 20 minutes. That's just going to be an extension of this lecture. And then that will be, you'll watch that, and it'll be the rest of lecture. And then you'll have your homework. But I want to talk about the mastery test. So in exam prep and solutions on Blackboard, you go to exam prep and solutions on Blackboard. I have a folder called the Mastery Exam. In that folder, there's two things. The list of rules. I showed you that. It has all the rules for different functions, and then the general rules for combinations of functions. So I showed you earlier. That's there. But what else is there is the problem bank for the exam. So the second half of the exam, mastery exam, you will get 10 of these problems. So I'm giving you all 48. You will find the rate of change function for 10 of these. Okay? So some of these, a few of these you're ready to start working on. After the 20-minute video, a lot more of them you'll be able to start working on. And then after Tuesday, you'll be able to, okay, can I have your attention, please? This is really important. This is about the mastery exam. So don't talk to your neighbor. Don't touch your neighbor. Just give me 30 seconds. Okay, so as you watch the rest of lecture, and then after Tuesday, you'll have the skills or have the training to be able to do all of these. Okay, so little by little. So, but they are posted now, and they won't be homework. But like I said, the second half of the exam will be 10 of these problems. Everyone will get a different 10. Okay, everyone will get a different 10. So just look on Blackboard in the homework section for the video extension and homework. Okay, have a good weekend. Here's one that uses all the rules we've learned so far. So let's give it a shot. But as we do it, we want to cite every rule that we use. So we come to this first. So as a whole, what rule are we applying to the whole thing kind of first? What rule applies first? Sum and difference. We have the sum and difference of functions. So each one of those, we're going to find the derivative of each one and take the sum and differences of those derivatives. That's what the sum rule says. Okay, so we come to the first one. What rule applies to the first one? I hear most people saying constant multiplication. We've got 4 times a function. So the derivative or the rate of change will be 4 times the rate of change of that. Okay? So whatever that is, rate of change is going to be 4 times that rate of change. Okay, 8 to the x. Rate of change. We just learned it. So exponential functions, we know are a constant times the original function, right? What's the constant? Natural log of the base that you started with. Okay? So I showed, in the rule I showed it before, so usually you write it after. Okay? X to the minus 8. What rule do we use? Power rule. It'll be? Okay, so negative 8. X to the, so the question is it negative 7 or negative 9? You literally subtract. You literally subtract 1. Negative 9. Okay? Plus derivative of x. Okay, so you can apply the power rule, or you can just think, oh, x is a linear function. It has what kind of rate of change? Constant rate of change. What's the constant rate of change of the function x? 1, right? So it's like m. It's like your coefficient is your constant rate of change. So 1. Or you can use the power rule. 1 times x to the 0. X to the 0 is 1, so you just get 1. Okay? What rule do we apply to minus 2e to the x? Constant multiple. It's going to be minus 2 times the derivative of e to the x. That's the one case where your derivative, your rate of change is the same as the function. We just showed that. Okay, x to the 10.7. So, I know many of you have done these before. So if you've never done these before, and I lose you, you have to ask, because I'm hearing 60% of the crowd just getting this right. So if you've never done this before, and I'm assuming that you're getting it and you're not, please ask, okay? So x to the 10 plus 7 would be which rule? Power rule. which would be 10.7 x to the 9.7. Subtract 1. Minus, we just showed that rule. Radical x is 1 over 2 radical x. Last one. Is it e squared? Okay, this is something that students miss a lot. Listen, in its nature, what is e squared? It's a constant. That's a number. That's not a function like e to the x. This is a constant or a number. So what's the rate of change of constant? 0. There it is. Okay. Okay, so we have not dealt with products and quotients. Products and quotients. So here's two functions, f and g. We can make two new functions. One by making a quotient of those two. So we could take sine divided by e to the x and make a new function. We could take sine times e to the x and still make another function. So what about the rate of change? So we had that the rate of change of the sum, say f plus g. So if I made a function, let's call it w of x. Okay, that'd be sine x plus e to the x. And for sum of functions, how do we find the rate of change? The rate of change of the sum, right? It was like falling out of bed. It's so easy, right? So what about the rate of change, say, of a product? We just do the product of the rates of change, right? And then the rate of change of the quotient. Just do the quotient of the rates of change. Calculus students throughout the ages have tried to do that, but unfortunately, it does not work. You can't take the quotient of the rates to get the rate of change of a quotient. You can't take the product of the rates to get the rate of change of the product. That only works with sum and difference. That only works with sum and difference. So wouldn't it be nice? Wouldn't it be nice? So let's talk about product. So if we want to figure out how to find the rate of change of a product, say of f and g, what do we do? You're just making up rules? How are we going to find out? Everyone write it down. We're trying to figure out what that's going to be for a rule for rate of change. So what would you do first? We should all know this by now. What would you write down first? Everyone do it. If you're not sure, you haven't been paying attention. Okay, did you write something down? What do we know for sure the rate of change of f times g is? So we can write it down. We don't have it simplified, but we can write down what the rate of change of f times g is. How many people wrote that down? Not enough. Not enough. Okay, this is what we've been doing. This is our derivative, our quotient, our difference quotient, right? That's how we find derivatives. This is how we find rate of change. The change in y over the change in x for a change in x of h. Okay, we've done this many, many times. Okay, so what do we do with this? Okay, so here's these red terms here in the middle, these two terms right here. I've subtracted this f of x times g of x plus h and added it. So it's really, the whole thing is really just 0. So it's still equal to what's above. Okay, why did I do that? Because it works. Okay, because it will get us the result we need. So if you notice, now we're going to, if we group together the first two now, we take that minus and group it with this and take the plus version of the new thing and combine it with that, then in the first two, you have a g of x plus h. In the second two, you have an f of x. So we're going to factor those out. We're going to factor those out of their respective things. Okay? So all I did was factor out g of x plus h. And then here, factored out f of x. So if you look, what do you notice right here? This should look familiar. And then, same with this. This first thing that I put a circle around. What is that? The rate of change of f. And this over here? Rate of change of g. So that's why you do this initial step, and then you combine them, group them the way we group them, and then if you factor out, the rate of change of f and the rate of change of g separately emerge from this technique. So there they are. So we have g of x plus h times the rate of change of f plus f of x times the rate of change of g. Letting h get very small, we get this. So we get the one function times the rate. So this is the second. This is the second function times the rate of change of the first, plus the first function times the rate of change of the second. So the thing about the product rule is multiplication, you can switch the order, and addition, you can switch the order. So there's like 8 different ways or 4 different ways to write this. Okay? But if you switch the order here, it doesn't matter. If you switch the order here, it doesn't matter. If you switch the two terms, it doesn't matter, right? So this is in the order of the first function times the rate of the second plus the second function times the rate of the first. The first function times the rate of the second plus the second function times the rate of the first. Okay, and so here it is in the using primes. Here it is using our R notation, but it's all of them are the same. Okay, the rate of change of the product is the first times the rate of change of the second plus the second times the rate of change of the first. So it's kind of a hard one to mess up because the order you can change the order and you get the same thing. Addition, you can change the order. Multiplication, you can change the order. So you just take one of them and multiply it by the rate of change of the other. Then you switch it and you add them together. Okay? Okay, let's do some practice problems of the product rule and the chain rule and both. So here's a function right here, f of x. And with these more complicated derivatives, we always want to identify the structure first. So what is it that we're looking at that will govern what rule applies? Well, this function is a product. It's the product of two functions. We call this first one g, and we can call the second one h. So since the structure's a product, in the most general sense, the product rule will apply. So a derivative will look like what? The derivative of the first times the derivative of the second plus the second times the derivative of the first. So we've got the first and the second. We just need their individual derivatives, and then we write it down according to this product rule. So what is the derivative of h? Well, that's pretty easy. G first. Derivative of g is just going to be 8x cubed minus 0. Derivative of h is going to be 6x. So now we have all the elements. We have g, we have the derivative of h, we have the derivative of g. So we just write it down. So the first times the derivative of the second plus the second times the derivative of the first. Basic product rule problem. Okay, let's look at another example. Okay, here's another example. Function f. Consider this an accumulation function. We want to find the exact rate of change function, which is the derivative. Always first identify the structure. So what is the structure of this function f? Well, kind of the big picture of it, or the structure of it, is square root of some function. What we have here is then chain rule, because we have initially x is going to be executed by the function g, then the output of g will go into square root. So we really have the chain rule. It's square root of g of x is the general structure of this. So what will this look like? Well, according to the chain rule, when x changes a little bit, g of x will change by its rate of change with respect to x. And then when g changes a little bit, then the rate of change will be according to our square root rule. So the overall structure of the derivative will look like this. This is our chain rule. The rate of change of the interior function times the rate of change of the exterior function with respect to the interior function. Now it's just a matter of identifying what g is and finding the derivative of g, and then just rewriting this. So what is g? G is our interior function there. It's what's under the square root. Okay, so what is the rate of change of g? Well, it's going to be the rate of change of this function plus the rate of change of this function. Well, what's the structure of that? The structure of that is a product. It's going to be the rate of change of this product plus the rate of change of sine. Okay, so now we need to find the rate of change of that right there, which is going to be first times the derivative of the second plus second times the derivative of the first. And then our derivative of sine is simply cosine. So let's see what that looks like then. First times the derivative of the second plus second times the derivative of the first plus cosine. So all of that right there is the derivative of this interior part, which we call g, or the rate of change of g. And we know the overall structure of our rate of change function will be this, and we've got all the pieces. We've got the rate of change of g, and we're going to do 1 over 2 times g. So when you write it all out, here's what you get. So the overall structure being the square root function with chain rule will look like this. So it's just a matter now of identifying g, finding g's rate of change, and plugging it into that form of the rate of change function for the square root of g of x. Okay, one more example. Here's an example, and we first ask the question, overall structure. What is the structure of this? Is it something to a power? Is it a e function? Is it a product? Which of those things is it? Well, its overall structure is this function to the 9th times this exponential function. Therefore, the overall structure is a product. So when we think of f, we're going to think it's a product of two functions I'm calling p and w. So this is function p, this is function w, and they are multiplied together, and that forms the structure of this function. Therefore, the structure of the rate of change function will be the first times the derivative of the second plus second times the derivative of the first. All we need then is these two rate of change functions, or derivatives. So let's do those. So what is going to be the derivative of p, or this one function to the ninth? Well, what's the structure of that? That's something to the ninth, but it will be chain rule because we've got this interior function. So by the chain rule, when you do the rate of change of that right there, you're going to start with the rate of change of this interior function, 3/4 x to the minus 1/4 minus 5 times the rate of change of the whole function with respect to the interior as it is. So it's going to be 9 times that thing to the 8th. So that's our rate of change of the first piece. Again, thinking about that our answer is going to look like this. That's going to, what we just found there, the rate of change of the first, is going to be right there in the answer. Similarly, the rate of change of the second. Well, what's that? The overall structure of that is e to the something. So we're going to start with that something. When x changes a little bit, 6 radical x changes by 6 times 1/2 radical x. So we're just doing the rate of change of this interior function, which is going to be 6 times the rate of change of radical x. So it's going to be 6 times 1/2 radical x times the rate of change of the exterior function with respect to the interior function. So that'll be the rate of change of e to the something is e to the something. So this is our rate of change of the second part, which we see here in the overall structure of our answer. So now we're ready to write everything down. We have p, the initial or the first function, rate of change of the second, plus the second, sorry, the rate of change of the second's over here. So plus the second times the rate of change of the first. So we have all the building blocks. You can just write it down there. So the overall structure of this is product rule, because that was the overall structure of the initial function. But within that product rule, we have chain rule. In the product rule, when we get to the rate of change of this part, it's going to be chain rule right here. And when we get to the rate of change of this part right here, that itself is going to be chain rule. E to a function will be chain rule. Okay, I hope these examples have helped. You should maybe take a break, go back and watch these 3 examples again, but instead pause the very beginning after you see only this function and see if you can recreate the derivative function the way I have without going through the explanation. So pause the video, try it yourself for these last 3 examples. Okay, good luck.